Hello everyone. So this is a question from JEE Mains 2026 28 Jan evening, and so we have been given A to B is the first reaction, C to D is the second reaction, and both are first order reactions. Okay, rate constant for first reaction at 500 Kelvin is double of the same at 300 Kelvin. Okay, at 500 Kelvin 50% of the reaction becomes complete in 2 hours. Okay, activation energy of second reaction is half of that of first reaction. If the rate constant at 500 Kelvin of the second reaction becomes double of the rate constant of first reaction at the same temperature, then rate constant for the second reaction at 300 Kelvin is dash into 10 to the power minus 1 hour inverse. Okay. So the chapters involved is chemical kinetics, and I will quickly write down the details that have been given to us. First, they have given us that there are two reactions, A to B. So let's say that is reaction 1, and C to D, let's say that is reaction 2. And both of them are given to us as first order reaction. Okay. Then they have given us that the rate constant of the first reaction at 500 Kelvin is equal to 2 times of rate constant of the first reaction at 300 Kelvin. This is the second information. Then at 500 Kelvin, 50% of reaction complete in 2 hours. Okay, and next information is activation energy of the second reaction is equal to half of the activation energy of the first reaction. Then rate constant of the second reaction at 500 Kelvin is equal to 2 times of rate constant of the first reaction at 500 Kelvin. Rate constant of the second reaction at 300 Kelvin. So they're asking us the value of this into 10 to the power minus 1 hour inverse. Okay, so this is our aim. So these things are given to us. That is, there are two reactions, both are first order. Then for the first reaction, the rate constant at 500 Kelvin is twice of the rate constant of the first reaction at 300 Kelvin. Then at 500, 50% of reaction complete in 2 hours, that is T half is given. Then activation energy of 2 is half of activation energy of reaction 1. Then rate constant of reaction 2 at 500 is 2 times of rate constant of reaction 1 at 500 Kelvin. So they are asking us to calculate rate constant of reaction 2 at 300 Kelvin. Okay, so before we go and solve this, we need to know few things. That is, for a general reaction, if we have a general reaction, that is A moles of A is becoming products. Okay, so we have experimentally observed that rate of this reaction may not depend upon all the A. So we know that rate is depending upon the concentration of the reactants, no doubt about it, but the power to which the reactant is raised may not be A. Okay, so we write rate is directly proportional to, yes, concentration of A, but the power need not be A. So we write something called alpha. Okay, and this, whenever we remove the proportionality constant, we write it as rate is equal to K into concentration of the reactant to the power alpha, and this is known as the rate law. This equation is known as the rate law. In this rate law, K is the rate constant, and this alpha may or may not be the same as the stoichiometric coefficient of the reactant in the balanced chemical equation. So alpha, it might be equal to A or it may not be equal to A. Okay, and this rate law is determined experimentally. Okay, and the sum of exponents to which the molar concentration in rate law equation are raised to express the rate of the reaction is known as the order of the reaction. Okay, so sum of exponents to which molar concentration in rate law equation are raised to express rate of reaction. So this is known as order of the reaction. Okay, so for example, in this case we have just one reactant, so therefore the order depends upon the value of alpha. So if alpha is equal to 0, then it will be a zero order reaction. If alpha is equal to 1, so it will be a first order reaction, right? So let us assume that there are two reactants, that is A plus B, giving us some products. We don't care about them, at least here. So let us say rate is like writing the rate law, rate is equal to K into A to the power some power alpha, B to the power some power beta. So the order is the sum of exponents. Okay, it is the sum of exponents to which molar concentration in rate law. So this is the power of concentration of A, this is the power of concentration of B. Their sum, alpha plus beta, is the order. Okay, cool. Now in this question, they have told us that both of them are first order reaction. Okay, so that's an important information. Then the next thing that we need to know is that quantitatively, effect of temperature on rate of reaction or on the rate constant. Okay, so effect of temperature on rate of a reaction or on the rate constant. Both are same only, because rate depends upon the rate constant, right? So it is given by the Arrhenius equation. Okay, Arrhenius equation is K is equal to A e to the power minus EA by RT. Okay, where K is our rate constant. Okay, A is our pre-exponential factor. It's a constant for a particular reaction. It is also known as frequency factor. Okay, EA is the activation energy. We'll see what is it. And R is the gas constant, T is the temperature. Okay, now since we have the Arrhenius equation, okay, so we take log of both sides of this equation. Okay, so when we take log, so it becomes log K log base E. So it will, log base E can be also written as ln E. So you can write it as log E or ln E. So ln K is equal to ln of A minus EA by RT. Okay, because ln E base E is 1, so the power is left, that is E minus EA by RT. Okay, so let us say that at temperature T1 rate constant is K1, and at temperature T2 rate constant is K2, because the rate constant depends upon the temperature, so its value will be different at different temperature. Okay, so therefore we can write ln of K1 is equal to ln of A. A does not change because it's a constant and it depends only on the reaction that you are taking. So minus EA, again activation energy is fixed for the reaction, doesn't depend upon the temperature. So EA by RT1, and ln K2 will be equal to ln A minus EA by RT2. Okay, let us say this is reaction 1, let us say this is reaction 2. So subtracting 1 from 2, we get ln K2 minus ln K1 is equal to ln A minus EA by RT2 minus ln A plus EA by RT1. Okay, so this ln A gets cancelled. So we know that ln of A minus ln of B is ln of A by B. So therefore we can write the left hand side as ln of K2 by K1 is equal to EA by R common 1 by T1 minus 1 by T2. Okay, so this is a very important relation, okay, where K2 and K1 are the rate constant of the same reaction. We should not forget that, at different temperatures, and those different temperature is T1 and T2. Okay, and upon solving it further, so we'll be getting EA by R, and when we take LCM, T1 T2 T2 minus T1. So this is the final equation that we'll be using it in this question. Okay, that ln of K2 by K1 is EA by R, T2 minus T1 by T1 T2. Okay, now in the question it is given to us that K1, that is rate constant of the first reaction at 500 Kelvin, is equal to 2 times of rate constant of the first reaction at 300 Kelvin. So two different temperature and different rate constant at different temperatures, obviously. So therefore K1 at 500 divided by K1 at 300 will be equal to 2, right? So I will substitute this in, I will use this equation. Okay, so I know that ln of K1 at 500 divided by K1 at 300, that is, rate constant of the same reaction, that is 1 1 at two different temperatures. So 500 is T2, 300 is T1. So it will be equal to EA1, because we are talking about reaction 1, divided by R. So T2 minus T1 is 200, and T1 T2 is 15 4 zeros. So 2 0 gone. So it will be left, you will be left with 750 in the denominator. So, and this is given to us that this is 2. So ln 2 is equal to EA1 by R into 1 by 750. Okay, or we can say EA1 is equal to 750 R ln 2. Okay, so this is some information that we have got, that the activation energy of reaction 1 is 750 R ln 2. Okay, now some prerequisite about activation energy, that it is the minimum energy, extra amount of energy absorbed by reactant, so that their energy becomes equal to the threshold value, that is known as activation energy. Okay, so I will write it down: minimum extra amount of energy absorbed by reactant molecules, so that their energy becomes equal to threshold value. So that is known as activation energy, which is represented by EA. Okay, so understand this. Let us draw a graph, okay, for a reaction. Potential energy, and in the y-axis, and reaction coordinate, that is, which tells us about the status of the reaction. By status of the reaction we mean whether it is reactants or products, or a mixture of reactants and products. Okay, so any reaction goes in this fashion. Okay, and this is the reactants and this is the products. Okay, so this is one kind of reactions. So let's say this is the reactants, this is a product, right? So this value is telling us the average energy of the reactants, right? So this value tells us about the average energy of reactants. And can you see, we have to cross an energy barrier, right? We have to cross this energy barrier. This plateau is the energy barrier that we need to cross, right? And this energy is known as, the value of this energy, this is known as the threshold energy. Okay, so this is the energy of, average energy of the reactant molecules, and this is the threshold energy that we have to cross. So therefore we have to raise the energy of reactants to this threshold. So therefore this value is known as activation energy. Okay, so it is the minimum extra amount of energy absorbed by the reactant molecules, so that their energy becomes equal to the threshold value. So this is known as activation energy. Okay, so we can also write that activation energy is equal to threshold energy minus average energy of the reactants. Okay, cool. Right, and we also know that time taken by the substance in which half of it has reacted is known as T half. Okay, so time taken by the substance in which half of it has reacted, so we know that that is known as T half. Okay, now for a first order reaction we know that T half is equal to 0.693 by K. K is the rate constant. Okay, or we know that 0.693 is also ln2 by K. Okay, now at 500 Kelvin, so it is given to us that at 500 Kelvin, okay, temperature important because K depends upon temperature. It is given to us that T half, that is the time taken by the substance in which half of it has reacted, is 2 hours. Okay, so we know that this will be equal to ln2 by K of reaction 1, obviously, and at 500 Kelvin. Okay, so therefore I can write K1 at 500 is equal to ln2 by 2. Okay, so this is an important detail. And we have found activation energy of the first reaction, that is 750 R ln2. Okay, so let's write that down. We know that activation energy of the first reaction is 750 R ln2. Now in the question they have given us that the activation energy of the second reaction is equal to half of activation energy of the first reaction. So therefore activation energy of the second reaction will be equal to 375, that is half of this value, so it will be 375 R ln2. So again this is one important information. Okay, and one more thing is given to us, that is rate constant of reaction 2 at 500 is twice of rate constant of reaction 1 at 500. Okay, and we know the rate constant at 500, that is equal to ln2 by 2. So we can calculate rate constant of the second reaction at 500. Okay, so it will be equal to 2 into ln2 by 2. So therefore the rate constant of second reaction at 500 is equal to ln2. Okay, now what is the question asking? The question is asking find the rate constant of the second reaction at 300, right? So to find this we will use this equation that we have derived. So this is a very useful relation. Okay, whenever you have two different temperatures and two different rate constant, this can be used to find the the other rate constant at the other temperature. Okay, so I will use this equation, that is ln K2 by K1 is equal to EA by R T2 minus T1 divided by T1 T2. We need to remember one thing, that K2 and K1 are the rate constant of the same reaction at different temperatures. Okay, they are not the rate constant of different reactions. Okay, cool. So we can rewrite this equation as ln of K2, that is rate constant of second reaction at 500, K2 at 300 will be equal to obviously EA2, because we are talking about the second reaction now, and temperature will be it will be 200 divided by 15, 0 0 0 0, so 20 gone, so you'll be left with 1 by 750. Okay, so and we know that K2 rate constant of reaction 2 at 500 is ln2. We know the value of K2 500, that is ln2, so I will write it down here. Okay, so this is ln2 divided by K2 at 300. This is what we are supposed to calculate, right? This is our aim. We also know the value of EA2. Okay, EA2 is equal to 375 R ln2. So we'll substitute the value there. 375 R ln2 divided by R, and we have 1 by 750. Okay, so this R gets cancelled and this is twice of that, so we are left with ln2 into 1 by 2. Okay, now one important property of log is that ln of a into 1 by, let's say constant 1 by alpha is actually ln of a to the power 1 by alpha. The power comes down. Okay, so we can write this ln of 2 into 1 by 2 as ln of 2 to the power 1 by 2, or which is ln of root 2, right? So you can see that ln of something in the LHS is equal to ln of something in the RHS. So therefore they must be similar, they must be the same thing. So therefore, ln 2 divided by k2 at 300 will be equal to root 2. Okay, because log of something is equal to log of something, so therefore this and this should be equal. Okay, cool. So ln 2 by root 2 will be equal to our k, rate constant of reaction 2 at 300 Kelvin. So this is the answer. ln 2 is 0.693 and root 2 is 1.414. When we do this calculation, we approximately get 0.49, right? Now in the question, they have asked us the answer with respect to 10 to the power minus 1. We got it as 0.49. Okay, so to get this value, that is 10 power minus 1, multiply by 10 power minus 1, divide by 10 power minus 1, because both will cancel out and we'll get 1 itself. Okay, so 10 power minus 1 in the denominator is actually 10, so it is nothing but 4.9 into 10 to the power minus 1, and when you round it to the nearest integer, this 4.9 is nothing but 5. So answer is 5. Okay, thank you.